Okay, good afternoon. This is the start of lecture 1B, as I'll label it later when it gets posted. So I really don't have anything new on the website except I did get the video link. It took some time to finally do that. The video processed through the night when I left. So I'll probably do that same thing today and I'll get it in the morning. One thing I did add though, and this is true no matter what web page you're on for me, is I updated that link where it says office hours. So I've got this up here now, and this kind of explains to you what my tentative office hours are. The teaching and the class office hours, those are fixed. But then I have meetings on certain days, like today I had budget committee meeting and a faculty meeting. The blocks that I have labeled research, consulting, search committee, those are just other duties, and they're just fillers. I mean, I'm going to try to do as much as I can, but if you want to make an appointment to see me during one of those times, just go for it. You know, send me an email and say, can we meet at this time? And if I'm available, I'll do it. Some of the other blocks you see on there, like the Harris team I'm advising, I'm meeting with them at 8. I'm going to meet with another team sometime, I don't know when, the radar team or ISAR team. Then I've got other graduate students, and I'm missing some graduate student meetings because I just didn't put them up yet, but I don't really know at this point. I guess what I'm trying to say is I've just guessed at things in some cases because I just know it's going to happen where the chip is going to lie. I'll drag it around and this thing will get pushed up again, and I'll change what's outside my door. But down at the bottom, I just say, make an appointment, and most people will just not use the phone. It's not really a very popular thing anymore, but send me an email and say, I'm really struggling and I want to come and see you. Like I said last time, some of you are probably going to say, I'm having problems getting Python and Jupyter Lab running, and I found a really good way is to just follow me to my office with your laptop and set it down, and I'll just kind of help work your way through it. That can be very efficient as opposed to batting emails back and forth. I mean, I'll try it, but if that's something you'd like to do, I'll definitely do that because I've seen a lot of different things before in that regard. So last time I left off at this slide, Communications Lab Connection. The lab has met yesterday, and a number of you are in the lab. And I think yesterday's lab session was by and large successful. I mean, from what I can tell, learning the instrument and following the instructions that I wrote into the lab document itself. At some point today, I may wander into that sample notebook just so I can kind of explain to you a workflow as to how you can take the notebook, get its results out, and then be able to, say, take it over to a Markdown in the Markdown editor that I recommended, Typora, and then be able to get a couple of pages that you can put in to a notebook and then render out to PDF, and then ultimately print those pages and make those be attachments to your handwritten, say, solutions or something like that. In other words, if I ask to do it in the Jupyter Lab, Jupyter Notebook, how do you actually produce that? Easiest way is to just go printing the web page, and that works fairly well too, but there's lots of different options. I don't remember, Chris, did you use Typora or did you use LaTeX?
Typora.
Okay.
I preferred it. It worked a lot better.
Yeah, it's a lot less, it's more convenient to set up. That's the main thing.
So I like the output too.
Yeah.
And the new table of contents feature.
Yeah, and I use that in various places. So in terms of other things in the lab, I think I went through that. We got a couple of, the lab grew a little bit yesterday, so I don't think I really need to say any more sales pitchy stuff about it. I think it's going well. But if you wanted to join the lab, you can still join the lab. There's not a shortage of stations. It's 1:30, and it goes until, what is it, 2:30 or 2:40 or something?
It's 1:40 to 3 o'clock.
Yeah, 3 o'clock. I was in there a bunch. Professor Semiari is going to be in there, and then Daniel Doty, who's the official lab instructor, he's in there. So we had pretty good coverage. Like that's why I feel like it went well. I mean, anytime you learn a new instrument, Spectrum Network Analyzer, it's a small little package, those of you that were in the lab, but it does a lot, right? It's simply amazing what it can do, and you are just starting to explore it, so don't feel daunted. Just say, I'll take it step by step, like anything. And then the function generator, you haven't really explored it too much, but it will generate modulated waveforms, and that will be very important in the later labs. And the main theme, though, is that Spectrum Analyzer and Vector Network Analyzer are capabilities that you don't use in electronics lab, although you can do spectrum analysis on these scopes if you want to, but the Spectrum Analyzer is an RF instrument, and it goes up to 6.5 gigahertz, so the ones we have at least, and it gives you a lot of capability for radio frequency stuff. Software tools, we have talked about that already. This was my old line, party line, I guess, was to use PDF export via LaTeX, but now I'm more advocating Markdown. To PDF, and I'll attempt to show that to you later today. PDF to LaTeX is the primo way to go, but it's just more fragile to get it set up. I have a new MacBook that I got, and because of changes in the operating systems and tool support, I cannot get scalable vector graphics, which I like in the notebook, to export properly anymore. It's broken. It still works under Windows, but until something changes in some open source things, it apparently is not going to work for the time being. But I'm fine with that. And the other thing is, I strongly advocate the Jupyter Notebook, but actually the app that you want to run, though, is Jupyter Lab. So and since I just scribbled out Jupyter, you're saying that's not the way it's spelled, right? Has anybody noticed that's not the proper spelling of the planet Jupiter?
It is not the proper spelling of Jupiter.
So why is that?
Why?
Yeah. So it's Julia, which is the JU, is another open source language that's kind of more like MATLAB, that it hasn't really fully blossomed yet. Python, and then the TER part are some other open source languages. R is one of them, so I think that's the R at the end, statistical language R. T and E, I mean, they're just, it's a concatenation of letters for tools that can run inside of it. I do want you, though, and this is why we're doing quizzes, you will get the opportunity to practice with your calculator and other tools that are available. Mathematica is very powerful. There's a couple occasions where I don't say run Mathematica on your system, although it's freely available. I say go run Wolfram Alpha. Has everybody played with Alpha at some point?
Wolfram Alpha, yeah.
Yeah, I have an instance where I might use it today, but there's one particular problem up in chapter 3. It's very handy to have. Now, Python has SymPy, symbolic Python, and it can do that, but Wolfram Alpha is so easy to access because it's right in your web browser. You don't pay anything for it. I used to, in the COM lab, I used to use ADS for block level simulation. I used to use Simulink. Right now in the lab, I'm not using ADS at all anymore. I just wrote it out of the labs last year. Not because I don't like it. It's just very big and powerful, but complicated to learn, and I'm trying to stay with the open source theme. So you're learning things about tools that you can take and use anywhere. And that's really a big deal. It's a big deal for me because that's what I do, and I go consulting. And if you go to industry and, this is what they give you, and you say, I'm sufficient, I can use open source tools, and I'm okay with that. That could be advantageous. Occasionally, a couple of times during the semester, it might be worthwhile to do LT-SPICE. We are going to go through an appendix at the end of the book that's called Noise Analysis, and that gets a little bit into circuit theory. We're looking at noise generated internally to electronics. And that's pretty much the reason why when I had the question last time about the noise on the spectrum analyzer window in SDR Sharp, remember you asked me that question, right? It's not that the signal is carrying a lot of noise with it, it's that the signal is weak and then there's a noise floor established by the electronics in the front end, and the signal is just sitting down close to that noise floor. There's nothing you can do to avoid having a noise floor, and it has to do with random electron motion in electronics, mostly just in a resistor, a simple resistor, and we'll learn about that in Appendix A, noise calculations. I said a little bit about COM1, COM2 sequence. So this fall is the COM2 opportunity. So what it adds on top of what you do this semester is random signal introduction, so you can model noise more properly using random processes. And that is not appropriate for this class because this class doesn't require that you've had 3610. Is anybody taking 3610 this semester? Prob and stats.
Oh, here right now.
Okay, so you have Dr. Semiari. He's giving you an incentive to use Jupyter, is what he told me yesterday.
Yeah.
Okay, well, I'm trying to get him aligned with my thinking because he's in my camp. I mean, I'm his mentor as a new faculty member, so that's cool. But you don't have to know that for this class, but I do talk about probabilistic things. And we'll learn about autocorrelation function and power spectral density, and those are typically defined for random processes, but we'll look at it deterministically in this class. COM2 also talks about coherent and non-coherent modulation in more detail and other types of digital modulation. We'll get brief introductions to those, mostly in the final project, but then also mobile radio channel, SATCOM channel, and some coding theory. But again, I had coding theory in the final project last year for this class. You just are plugging into it and using it. And Dr. Semiari may use some coding theory examples in prob and stats, just in probability equations. Just a quick little comment on that. Coding theory can be as simple as just repeating something multiple times. So we actually use coding theory in our everyday lives in kind of an abstract way. If you're in a really noisy environment, they call it formally the cocktail party problem when you're in a crowd with a lot of people just trying to talk. What do you do if you can't hear somebody? You ask them to repeat it, right? So a simple coding scheme is just repeating multiple times, and then you increase the probability of getting a correct reception. If you repeat 3 times, then you can take the, say it's ones and zeros, so if the message is a 1 and you receive 2 ones in 3 attempts, what would your inclination be? If it was 2 ones and a 0, your majority vote would say it must be that you sent a 1. So it can correct 1 error. The problem with repeating, though, in a communications efficiency standpoint is you're either going to send your information at 1/3 the rate, or you're going to send it at 3 times the required rate, which is going to occupy more bandwidth. So that's what coding has as a trade-off, but coding does give gains. It more than rewards you if you code properly. Repeat coding is not very efficient, but there's other schemes that are very efficient. So needless to say, they're used in cellular telephony. When you talk on the phone, your speech gets digitized in a speech encoder, and then it gets encoded with a forward error correction, and then that helps things when you receive. Okay, the author of the book, Dr. Zemer and Dr. Trander, and I think I told you Dr. Zemer was my dissertation advisor. He was department chairman here. I think it was starting in 1984. Right after I graduated is when he started here, and then I came within a semester. And the other author of the book, William Tranter, they both taught at Missouri Science and Technology, which is Missouri School of Mines originally. Dr. Zemer, as I said, is not doing fantastic because Parkinson's is taking over his body, which is a progressive disease, and you might have a family member, know somebody, you might know about that disease. It's devastating is what it is. It's progressive, and it just, well, it does bad things. Different than cancer, because cancer can kill people really fast. Parkinson's tends to just slowly eat away at you. Dr. Tranter, though, went to Virginia Tech to teach. About the time Dr. Zemer came here, Virginia Tech happens to be where Professor Seminari got his PhD, so there is sort of a roundabout connection. Dr. Tranter, though, passed away within this past year. I never had him for a class when I was at Missouri S&T. He was a very funny, he's a funny guy that was a great lecturer. People really liked him. But I'll have to say, he never was in the greatest of health. The whole time I saw him, he was kind of overweight and just didn't seem like he took care of himself really well. So it's sad, though, that he's no longer around. In this book, I like the book, but the book is, you know, the 7th edition. I had classes from this out of the 1st edition, so I've been acquainted with it for a very long time. But it's like everything, it's passing away too. I mean, the book is still valid, and this edition's only been out for a few years now, but something else will happen, and we'll change books at some point. But do you guys ever think about that? How engineering books have a time, and then they kind of fade away, and then something else comes in. Certain books stay around a really long time in technology, but not that many of them. So, pardon me?
March of progress.
Yeah, and we don't really notice it because we are in that timeline moving along, so we don't really look back and think way out in time, what book are they using right now? I have my trusty book that I keep referring to, and I like it. I don't want to replace it, and that's just kind of the way we are with books that we learn things out of. Okay, what are some important dates in communications? And this will be wired and wireless. Transcontinental telephone, 1915. World War II is when radar and microwave systems started coming into being. The transistor, 1948. First SATCOM, Telstar 1 in 62. Fiber optic communication started to take off in 1977. And I'm going to pass this around in a second. This could either be a large spool of fishing line, you know, for putting on your fishing pole, or this could be fiber optic, and it's fiber optic. So I'll explain that a little bit when I get to that. Global positioning system completed in the 90s. When I originally started my first position at Motorola Government Electronics in Scottsdale, Arizona, that was around 1980. That's when I worked for a while in industry before I went back for my doctorate. The group I worked in was building parts of the GPS satellites, and other divisions within the plant that I worked did other things for GPS satellites. And I know you're saying that's such a long time ago, you've got to be really old, and it's all, you know, it's all true, but it's not really, it hasn't been around for all that long a period of time. And you just can't remember what it was like without GPS though, right? Because it's always been there, and it's very pervasive. And now we worry about what happens if we have things bad happening up in space. I mean, so that's why we now have the Space Force that the president announced, and we've been doing things to try to protect satellites for quite some time from damage. It's been something that people have thought about, but so if the GPS satellites get wiped out, what's going to happen? Not that we need position location as much, but the GPS satellites are a time base that pretty much all our modern technology references. Every cell tower has got a GPS antenna on it, and it uses that to get time coordination. So that's the thing that most people that I know are worried about. If our GPS satellites are gone, we don't have the same time coordination, and things that rely on that go totally out of whack because they're not time synced anymore. So that's probably one of the biggest things about it. It's not that your watch won't have the right time on it, because that's tied to GPS clocks too, but it'll cause issues. Long-term evolution, which is the 4th generation cellular that we use, that was around 2011, 2012. I'm not sure that it was here in Colorado Springs. Remember last time I was talking about how it was up in Denver first, and I think 5th generation is going to roll out in a similar fashion. Does anybody have a 5G phone? Where can you use it right now?
Boulder and Springs, but it doesn't really pick up in Denver. Actually, it gets good coverage in Ramos, Colorado.
Okay.
Though it turns on and off usually.
But it's
Which one?
The football stadium.
Oh, in Denver.
Yeah, because all the football stadiums are supposed to have 5G.
And I know I get 5G when I'm around it.
okay. I'm not really super excited about it. I could be. I think Dr. Semiari is interested in cellular. I did cellular stuff quite a while ago, and then I switched back to government, SATCOM and other types of work. But it's a progression, and there's a lot of different aspects of 5G. It's not just simply one thing like we think of with LTE. There's different bands and different services. Okay, the block diagram of a basic comm system is, this is what's in the book. We have an input transducer, and so we have an input message that may go through some sort of a transducer. So if it's an analog message, then the transducer would be a microphone or some analog to digital converter. And then the message signal might be an analog signal, or it might be a digital signal that's converted to, an analog signal that's converted to a digital waveform, but still it's going to be some waveform type of message signal that's going to go into the transmitter. It could be a purely analog signal, or it could be PCM encoded, so it's ones and zeros, but it's actually a waveform. It's something that goes into a transmitter, and then we have the modulation process taking place. And this will be talked about starting in chapter 3 more formally, but the model that we're going to see in the very beginning will be something like some sort of generic form like that is for a carrier-based transmission system, where the message signal can get imparted strictly into the AFT, or it will get imparted into the theta of T. So for us, chapter 3 is dealing with it going in there, and chapter 4 is dealing with it going in there as theta of T. But that's carrier-based systems, where you're going to actually put the information onto a high-frequency carrier and use that high frequency and a small, relatively small antenna to efficiently propagate it from point A to point B. It doesn't have to be on a carrier. It could be baseband. It could be have you ever thought about what's in the Ethernet cables that roll around the campus? When you are in a wired device these days, you plug an Ethernet signal in. So, a baseband Ethernet cable would contain signaling that's at so-called baseband, and baseband means it's basically at a carrier frequency of 0. Wi-Fi is not that case, though. Wi-Fi is on a carrier frequency, and then the digital modulation is imparted as a message signal, and so on. And then there's other things too. I was involved with optical communications, so optical communications, you could take the carrier frequency FC there and say it's the frequency of light. It was green light that I was involved with, and it was polarization modulation, but it also involved intensity modulation. So it involved in changing the intensity of the laser light and then having it conveyed over two different polarizations. It goes through a channel, whether it's an RF radio channel or a baseband channel like the twisted pair cables. And it arrives at the receiver with some impairments, some time delay, some uncertainty about it. I taught the phase lock loops class yesterday morning, so I was talking to them about the fact that, like I told you guys on Tuesday, that the clocks are going to be asynchronous because we don't have a magic genie to take that synchronous clock signal unless we choose to send it on its own radio channel. We might choose to send a pilot signal. And I was talking, I guess that was an example in phase lock loops, a pilot signal. You might choose to send a pilot which has the required clock signal embedded in it, and then we can use that to unlock everything else. But generally in communications waveform design, you try to make things very efficient and not put a lot of power into sending the magic genie kind of a signal, because that kind of defeats the purpose of being efficient in communications. But in some schemes, they definitely do that. And it just depends. Deep space, they're not going to do that, because in deep space, if it's an explorer mission or something going way out to a planet, that's very limited power on that satellite from solar, and they want the power to go into the information varying waveform, and then they'll go to extremes to try to get synchronized to the signal. But the important thing is to get enough power in the transmission itself. If you had to put up a clock signal and the data waveform, that's robbing power just to send the clock signal. So rather be challenged with trying to derive that. And then coherent communications relies upon the need to phase lock to things, and that also gives you power efficiency. A 3 dB power efficiency is definitely a welcome sign, because 3 dB can change the difference in error probability by somewhere around 3 orders of magnitude. It could be typically less, but you have a waterfall curve that describes the probability of a bit error versus the signal to noise ratio at the receiver. And in the steeper part of the curve, or especially with coding theory involved, the curve drops off like a waterfall. That's why it's called a waterfall curve, and we'll be seeing those later in the class. But so a few dB of difference in the link budget or link margin makes a huge difference in the error probability, and hence, reliable transmission of information. Different channel types are out there. The most common is electromagnetic wave propagation in the microwave frequency bands, RF, all the way on up. I mean, I guess where I went to school at Michigan Tech, which is in Upper Michigan, Michigan School of Mines is located there, if you've ever heard of that school, because they used to play Colorado College in hockey, but they don't come here very often anymore because of the leagues and everything are different. But at any rate, that school is pretty isolated, and the Navy was interested in using the hardwood forests up there to set up a giant antenna system for talking to submarines. And it was low frequency. It was like 40 hertz was the carrier frequency. You don't send a lot of information quickly, but if you're trying to talk to a submarine about critical missions, you can still tell it what to do and what not to do, what to launch, what not to launch. That makes sense? It was ELF, extremely low frequency. And it was quite a bit of power, so it actually used the whole Earth as an antenna. And I remember when I was in school, they were concerned that that was going to do something to the forest. So the forestry program up at Michigan Tech started monitoring tree growth and rings in trees to see how they were separated. And I think that they found, this is vague in my memory, that things were growing faster. So the trees grew more when the RF was around them. But I don't remember that specifically. Type Google ELF and health, or ELF and plants or something, because they set it up in the forest. I mean, it's buried in everything. But curious, because we now have microwave devices around us no matter where we go, and you can't really even avoid them if you chose not to use one. Where can you go where it's not prevalent? I mean, we're standing here, Cheyenne Mountain's over there. There's a lot of RF coming off of that. So fundamental modes are ground wave propagation along the surface of the Earth, so that tends to follow the curvature. We have line of sight propagation is probably the most common that we're familiar with, and that's just showing a ground station to the aircraft. Then we have things that penetrate through the ionosphere, and that would be SATCOM communications. So it's called trans-ionosphere line of sight. It's at a high enough frequency that the ionosphere does not block it, just like in a microwave oven. You've got the grid there to block the microwaves, but the ions that in the ionosphere are not dense enough for these high frequencies that they block those short wavelengths. But for lower frequencies, then the ionosphere acts as a reflector, and then we get skip wave propagation, which is something that's also shown in this picture, where at night the ionosphere gets denser and tends to go, the layer that's got the dense ions in it is up a little bit higher, and then you can propagate signals for a great distance. And has anybody not ever experienced that, being in your car at night, turning on the AM radio and listening to stations from like New York City maybe, or Los Angeles? If you haven't done that, do it sometime, because it's interesting. I mean, the FCC regulates what stations can stay on late at night because the AM signals skip a long ways. They travel a great distance. So there's only certain stations that occupy the AM radio band, and then they get reused when you go to a different locale, like we were talking about last time. So because AM travels so far at night, there's only local AM radio stations have to reduce their power so they don't travel as far. And then the super AM stations, like the ones that were first in existence, are what are called clear channel stations. They get to stay at full power, and they broadcast all through the night. So those will be, Denver KOA, I think, is one of them. So KOA is a clear channel station. Then there's Chicago stations, New York stations, and Los Angeles stations. There's probably one in San Francisco, but those are the stations that you can get late at night that are a long ways away. I mean, you're still going to get the few AM stations that are on at low power, but what you're interested in doing is seeing what you can get far away. And if you're an amateur radio person, I think the slang term they have is DXing. Has anybody ever heard that term? They're trying to, I can't, my father did amateur radio, and that's why I got interested in radio, but it means something. I can't remember. I probably knew at one time. But you're just trying to listen around and see how far away you can hear something. And if you go to the shortwave radio bands, which are up higher in frequency, between 2 megahertz and 30 megahertz, you'll hear stations from around the world up there at night. So it used to be a hobby. You'd buy a shortwave radio because you want to see what stations you can get from around the world. I don't think it's a really popular hobby anymore, but it's fun. I actually have an adapter for the RTL SDR that allows it to receive lower frequencies, and then I have a long wire antenna that I can set up in my house to do that.
What's the range of the RTL?
Receiving wise, the reception, it's only a receiver. It seems to be quite sensitive to me. It's much more sensitive than the Pluto, which I brought in here, because it was designed for digital video broadcasting. And I think it was designed for Europe and I guess Japan, some of the other markets is what brought it into existence. And I don't know, I mean, I know to get a quality HD signal off of Cheyenne Mountain, and I have cable at my house, it takes more power to get that higher quality signal to your home. So I'm guessing these receivers were sensitive enough that you wouldn't have to be right on top of the station. It would be probably in your community, though. I just don't know how sensitive, but you can play with it when you do lab number 6 in the comm lab. Works with the RTL SDR a lot. Electromagnetic spectrum is a natural resource, so it's something that not everybody can use frequencies at the same time. And I think I have a picture in here. If not, I have to download it. I have the Nerd Dork Geek Venn diagram. Has everybody seen that Venn diagram? You want some light comedy? Does it have your curiosity peaked?
Absolutely.
Okay, you need to see it. My wife gave this to me a long time ago. She was a programmer at FedEx. I'm not asking you to classify yourself, but it's just interesting.
It's funny, I don't see neckbeard on there anywhere.
Really?
It's probably right around Dork.
Yeah.
Yeah.
Yeah. Smaller circle within the circle.
Yeah, exactly.
So just think about that. I mean, I don't hate to say this, I just have to say it. If you're in engineering school, you go to graduation, which you'll hopefully do, and you just look at the clustering of people lining up for graduation, and engineers tend to really stick out because they are who they are. I mean, I'm an engineer, but neither of my sons got engineering degrees. One son is an architect, the other one did a health and exercise science. And so when I went to their graduations at K-State and Colorado State, the schools they went to, my wife, who's also an engineer from Colorado School of Mines, said, "Those are the engineers over there, aren't they?" You can just tell because, engineers are there. And I'm not picking on any of you because I'm in the same category, but it's just, I don't know. I guess I know I'm obsessive about things because you want perfection. Okay, enough of that. I generally don't show that, but I happen to see it right there. I was going to go look for the chart. I think I can probably find it pretty quick. If I can't, I'll give up on it. See, I typed NTIA, National Telecommunications Industry Association, and look at that, just a little ways down. NTIA has an office up in Boulder, so we gotta be able to get to the chart here pretty quickly. But maybe I won't find it really quickly. Well chart, there it is. It's the same spot, there it is, okay. It starts at 0 kilohertz where it says it's not allocated. There's radio navigation a little ways up there. starting at 9 hertz, I guess, or 9 kilohertz. But then it stops at 300 gigahertz. I'm not gonna, I could zoom in on any part. I encourage you to just go maybe take a look at this so you can see how the spectrum is so packed in with stuff. If we looked around 2.4 gigahertz, we'd see not just Wi-Fi, we'd see a lot of other things. There's industrial, scientific, and medical bands, which are unlicensed bands, which are scattered around as you climb up through the spectrum. But I could just zoom in around 2.4. It's this ISM 2450 is where Wi-Fi resides, somewhere in here. Amateur radio's got some things, but interesting. I mean, if you're a communications person, this is kind of your livelihood, is utilizing the spectrum. And pardon me?
A lot of people want to do a lot of stuff.
Yeah, it's a big thing. It's a really big thing.
So why do you have different colors on the same column? Is that they're sharing?
It might be.
Multiplexing it?
I don't know. There's probably a key over here somewhere. It's just
To look at.
the colors just tell you what type of usage it is.
So that's a lot.
Pardon me?
Kind of seems like we're running out of reasonable frequencies that don't.
Yeah,
hurt people.
absolutely. That's where 5G is trying to go up to the millimeter waves, because a fact of RF circuit design and just RF in general is what you can do on a given carrier frequency is a function of the so-called fractional bandwidth. So if you're at 10 gigahertz, 10% of 10 gigahertz is 1 gigahertz, right? Did I do that right? But 10% of 10 megahertz is only 1 megahertz. And so bandwidth is what matters. You can send bits per second per hertz of bandwidth if you have more bandwidth. And if you're at a higher carrier frequency, you can send more, right? And that's what 5G brings in, the millimeter wave stuff. But
Is that terahertz?
no, it's 30 gigahertz and things like that. But the thing is, only certain bands are good for propagating efficiently indoors. You know, higher frequencies don't propagate very well indoors. The media, the walls, and all that stuff interferes with it a lot. So
Sounds like an architectural problem at that point. Or-
somewhat. I mean, materials and causing,
Material engineering.
yeah,
I mean, we should be able to facilitate that with,
better different materials.
oh yeah, different kinds of paint, material coverings,
Yeah, but then outside you've got multipath issues and the reflecting off of natural things and
People
other
have been
objects.
Working out multi-path issues for years.
Yeah.
Done amazing work.
That's at 1.575 gigahertz where that sits. It's just, yeah, there's just an awful lot to it, and it makes it exciting. That's what makes it interesting. I mean, trying to utilize a natural resource, which is really what this is. So, and we're nearing, kind of capacity in a lot of areas. So, I've had students study cognitive radio, and cognitive radio is where you have spectrum sensing going on, and the owner of the spectrum that holds the license, and they pay money for those licenses, and the unlicensed bands are the ones that we use for our fun stuff, but the licensed bands are held by all kinds of services. I mean, just think, every TV station does remotes, and they do remotes with microwave, so they have a license to operate in a band for TV remotes, let's say, or other services of that nature. They don't share that spectrum. Once they buy a license for a region, they own it, and they're the sole user of it because they've paid for it. Just like the cellular tower frequencies, those are owned by the service providers. You are riding your signal on it, but that service provider owns that band, A, B, C, D, whatever, in the PCS band and so on, and they had to pay a lot of money for it. But cognitive radio says, okay, how can we fill in the white spaces? And that's what they call it, white spaces. So white spaces are when they're not using the band, could we just sort of hop in and use it, and then we're spectrally sensing, and as soon as the owner comes back on, we'll go quiet and we'll back down. So that's something that people have been studying now for more than 10 years, cognitive radio. And really cognitive radio, and it's, to me, cognitive radio is already being utilized, because if you buy a router, a Wi-Fi router for your house, when I first set up my first Wi-Fi router, I had to put it on frequency, what I wanted to use, and essentially nobody in my neighborhood had Wi-Fi. I didn't bring home a spectrum analyzer, it didn't have spectrum sensing. I just set it up, and when it worked well, I just said, okay, good. But now what a Wi-Fi routers, almost all of them, I think, do it, they spectrum sense, and they figure out a good spot to put the carrier frequency for your Wi-Fi, which Wi-Fi band to use. True? I know in my neighborhood I can see just a few users, but if you're in an apartment building, it's just crazy, 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 crazy. So that is, to me, that's a form of cognitive radio, because cognitive is cognition, being able to sense your environment and decide where should I be to avoid other close, strong signals. And I'm in a band in my house that I'm not really happy with. I got stuck with it. I mean, my router tends to like finding that. We moved it in the house, but we got a new microwave oven. And when the microwave oven turns on, because ovens use the same ISM bands, Industrial Scientific Medical Band, it jams the Wi-Fi at 2.4. And I brought home a FieldFox spectrum analyzer, or I actually had one at home, right? I told the guys in the lab I had the equipment at home when I wrote the labs last year. And I verified that, yep, when that microwave oven is on, there's all kinds of splattering around 2.4, and it's right on top of the Wi-Fi band that we were using. And then I looked at 5 gigahertz, which is around 1 octave above. You know, an octave is a doubling, so 2 times the 2.4 puts it close to 5. And it was wiping out the 5 gigahertz band as well, so I was kind of frustrated about that. But at least I could verify that it was there. And then I started checking to see that the microwave oven itself didn't have too much leakage, and Dr. Kelker told me he has these little inductive loop antennas that I could go around the seal on the microwave oven and see if it was leaking too much microwave stuff. I didn't do that, but microwave ovens have to attenuate enough, right? We don't want to have an oven that's leaking too much microwave power out into our bodies, or our eyeballs is what I worry about, because ages ago I toured a radar station in Upper Michigan, and heard the stories about how when Air Force personnel were working around some of the high-power radar stations, they ended up getting in the beam frequently, and then they developed cataracts at a very young age because enough heating was going on in their eyeballs from the microwave power. Doesn't sound pleasant, does it? But I've had students that have ignored their type 2 diabetes and haven't taken care of their sugar issues, and I had a student that got cataracts in both eyes as a result of not heeding the warning from his doctor. And for him, he doesn't recommend anybody do that, but when he got cataract surgery, he got new lenses put in his eyes, and so his vision was better than it ever was natively after the cataract surgery. It just sounds, I don't know, when he told me that, I was kind of like, that's crazy. So take it seriously if you have type 2 tendencies. Okay, we have names we give to bands. We have VLF, was a name used for very low frequencies, and ELF, extremely low, is what Sanguine Seafarer, the program, was talking about for the Navy. So I guess that was maybe, yeah, that was 40 hertz, so that was ELF. We also have other designators. I mean, we have the designators in that pinkish, or not pinkish, but orangish column. And I tend to side with those because those are what I grew up hearing in my house, being that my father did amateur radio. So HF, 30 to 30 megahertz, VHF, 30 to 300, UHF, 0.3 to 3 gigahertz. And then we've got, this chart goes all the way up into light wave bands, but the more common things for the microwave bands are the letters. So we have like L band is where GPS resides, because GPS resides at 1.575 gigahertz. We're in S band when we're talking about Wi-Fi. It sits inside of there, but S band is radar and other military applications. So, and then KU band is popular in other satellite applications, SATCOM stuff for commercial and military. And it also, or I covered the wrong one, X band is in there too. But and then just like in the United States, we tried to go to the metric system and give up using inches. We never managed to do that because I learned about it when I was in grade school. We're going to go metric. What do you guys think? Are we metric right now? I don't really think so.
I don't know, we do an awful lot. We do an awful lot in metric. We just deny it when we get to engineering.
Right, we just talk in American units.
Yeah, I mean, I do some things on my car. So I have English socket set, and I have a metric socket set. I have, English box wrenches and metric box wrenches. So I do have some of that because when I got my first Japanese car, I had to get metric tools to do things on it.
Yeah, no, it's ridiculous. Like everything's an architectural scale, in most of the engineering stuff that I do. But like even with like surveying, they take a foot and they divide it into tenths. So you have a tenth of a foot, and you actually have a tape measure.
Really? Okay.
Down into tenths and hundredths.
Most of us people don't even do that. I'll have to ask my son about that. I'm saying all that because these letter designations here is what they were advocating that we start using, those letters as opposed to the letters on the left. But it just hasn't really caught on in the military and naming of everything. I'm not going to really spend any time on this. This just gives you some other names. I've mentioned ISM, so you can see, I'll just show you that ISM bands, though, are up and down. They go up higher in frequency. We have the one at 5 gigahertz, and that's not in this chart, but there's another one at 900, and the one down there around 40 megahertz for heaters and welders. I don't do welding, but I guess I'm told up in the Northwest where they make a lot of plywood that the industrial heaters that they use to fuse plywood sheets together, that creates quite a bit of RF radiation or interference. Has anybody ever heard about that? A factory like Weyerhaeuser or somebody. I visited there with my family this summer in Oregon and Washington, and definitely saw a lot of wood product places. They've got a huge number of trees. They make our forests in Colorado look pretty lean. I mean, the trees there grow really tall and they're really thick, whereas here they're beautiful looking, but they're just not dense like they are up there. At any rate, there's that, and you can see you can just see what I was talking about. Microwave ovens are in there. Okay, how do we manage this? We have the FCC for the U.S. For the world, we have the International Telecommunications Union, and it holds conferences and things. This is just organized allocation of spectra. And realistically speaking, that's a very good thing to have, but in a time of a war or a really bad situation with military action, what do you think is going to happen? People are going to do what they think they have to do. So I'm not advocating that. I'm just saying that historically, pardon me?
So survival is survival.
Yeah, exactly. And we had an example of craziness a couple weeks ago with the thing in the Iranian thing going on, which I feel sad about. I feel especially sad that a plane got shot, a commercial jet got shot down. I mean, that's our technology world, though, right? Dumb things can happen, and other dumb things have happened over time.
Somebody really dropped the ball on that one.
But other things like that have happened before. That's what's so disappointing.
Yeah, that one was particularly bad though. I mean,
Yeah, it
all
is.
they do is stop air traffic because they knew they were going to engage that system.
Yeah. I don't know. I haven't talked with Professor Seminari about it because he's Iranian, but I don't know what he thinks about it. I guess I don't really want to know because it's just an unfortunate situation. Okay, talking a little bit about SATCOM now, which goes up higher in frequencies, and our millimeter wave stuff for 5G. So this is just something interesting to be aware of. When you are going up through the ionosphere, you don't want to be blocked, but the ionosphere is not going to block these microwave frequencies. But other factors come into play in propagation. We've got oxygen molecules resonate, and they block signal. So we have the resonant frequencies for oxygen and also for water vapor. So they have certain bands that you have these things going on. Now, and then we also have attenuation due to rainfall rate. So during a heavy thunder shower in one locale, satellites might not be able to downlink with their existing link budgets because heavy rain can wipe things out. But then another city will be able to pull it down, so it's not like it wipes everything out, but it can interfere with satellite communications. An interesting aspect of the water vapor and oxygen, though, is suppose you wanted to have a crosslink up in space, that if there was a possibility of the beam having a side lobe that would come down onto the surface of the Earth, using one of these resonant frequencies could actually be a good application, right? Because that way it stays up there and you can't eavesdrop on it from down below. In the program I worked on, the Green Laser Light program, the Air Force program called LaserCom, that was one of the reasons why it was going to go up into space, because the beams were so narrow that you could have laser crosslinks to have great security. And then another application of the green laser light was blue-green lasers for talking to submarines without having them have to surface, because it would penetrate through seawater more effectively. And I think we do things like that, but I don't know the details of that. I kind of got out of the optical stuff. When I left school, I got into optical just because that was what my master's project was on. And then I got involved with LaserCom, and all of the older engineers where I worked said, basically they said, son, you're going into a good area. Optical communications is hot and everybody's going to be doing it. Guess what? It sort of fizzled right out. They couldn't get a stable green laser to fly in space. But it's gone through cycles, and I just sort of lost contact with it. It did not destroy my career. It didn't really help my career, though. It was interesting to work on it, though. I was at White Sands Missile Range when it was being tested on the ground, and then an aircraft flew and talked to a ground station, and we sent a lot of bits per second, 1 gigabit per second. And I guess I'll say the coolest thing was working there at night in the desert and having the airplane fly around and seeing what looked like kind of a green light up in the sky. But then when that green came down onto the dome where we were receiving the signal, there was this eerie kind of green scintillating laser light that was coming down. So it was kind of cool to be involved with that. That system tracked, though, with bidirectional linking, so infrared went up to help point from what was in the aircraft, and that was very powerful beacon laser. And didn't I mention the beacon laser in here or not? Did I say that? I said that somewhere else recently. I guess the beacon laser was high power infrared, and when I was in the ground station working with the receiver that I was part of, and when they were doing a full transmission, in other words, they were flying a red light was flashing, and we had to have our safety goggles on that blocked infrared, because there was infrared leaving that facility going up into the sky. And infrared, because we can't see it, but yet it's powerful, it could cause eye damage. And it was during that part of my career that I read about eye damage and what a laser, high-power laser does when it gets into your eye. You think the cataract sounded bad. The laser light is really bad. It happens very fast, and it just melts everything. It's gone. It's gone just like that, pretty much. So if you have a laser pointer, I take that stuff seriously. I don't. After reading what happens when your eye melts on the inside, it's not very pleasant sounding. Okay, we have guided wave propagation, also twisted pair, coax cable, which I mentioned. Communications also gets involved with magnetic recording channel. We use that a lot over history. We maybe don't use it quite as much, but it's still out there. And then we have optical channel. And optical could be free space, like I've just been talking about. It could be fiber optic. And at one time, CDs and digital video players were really popular. That's kind of been taken over by streaming, right? You stream a program or a movie or something. But that doesn't take optical out of the picture, because that's our backbone in our country, is fiber optic. So I'll just pass this around. I got involved with fiber optic before I left industry, because I did some high-speed stuff with it. This is single mode fiber, and it's not sheathed at all. So it's very, very fine diameter. And I'll pass it around. The thing about single mode fiber is the attenuation. And this is a very old spool, but it says on the side it was designed to operate at, it's a waveguide, it's an optical waveguide, at 1300 nanometers. The attenuation is 0.8 dB per kilometer. So, pretty small, right?
Yeah, no, that's fantastic. Especially when it's given in units per kilometer.
Yeah. So the end of it's right here. It is glass. I've never known anybody to cut their finger on it. It's made by Corning Glass Works or something.
It's not insulated, so.
I think it was just a sample. The stuff that I worked on was a different type of optical fiber, and it was in a sheath.
Yeah.
And I had a spool of that was 1 kilometer, and I had experiments that I did when I worked at Motorola in Scottsdale, Arizona.
Yeah, 'cause the stuff that we're using for our project is shielded and has little ink caps on it and stuff.
Yeah, that's just raw fiber is all it is. How did I get it? When I joined UCCS, it was sitting in my office. I mean, it was sitting there. I don't even know where it came from. I just said, oh, I can use this as a prop. So I continue to, it's just interesting, right? But it's wiring our country together now. It is our backbone for all our high data rate stuff. I can't underestimate to you how significant that is. That is what makes us be able to do what we do. It's not being carried through RF, it's being carried through the fiber network.
Haven't they been laying fiber cables in the ocean too to replace the copper?
I think so, yeah. So, and of course, the internet is good and bad, right? You can get hacked. I mean, it's just a technology we brought in. I mean, engineers brought it in, and we maybe don't think about. We just think about the good it can cause, and then we don't always think about the bad it can cause until later. So. Yeah, exactly.
Well, yeah, the real advantage is to bundle those together, get a couple hundred of them, and the transmission rates are insane.
So we're just about out of time, and I didn't get to any math yet, so I'm going to skip this, the OSI model, Open System Interconnect. You've probably heard of it before. I'll just only say that where we're at in terms of the OSI model, we're right down here in the physical layer. That's what this class is all about, physical layer stuff. Low-cost software-defined radio. You can look at this. You'll see this in Lab 6 if you're in the lab. This is what I demonstrated last time with SDR Sharp. Very last thing in this chapter, though, is something that I found a few years back. Forget when did I find it. I didn't put the date in here. But I thought this was particularly interesting to me because this is like everything in a very tiny space. This is wireless in the eye, and this was for glaucoma patients. Some of you might have a family member. I have a friend at my church who's got glaucoma, and it's not curable. So we have too much pressure in your eye, and it just is something that can go out of control, and eventually you're blind. But when you go to the eye doctor, you have a glaucoma test pretty much every time, or at least when I go.
And they shoot the air in your eye.
Yeah, it's not a pleasant thing, but they're trying to figure out if you might have it. So this is really tiny, and it was something that could be put, as it says, interocular pressure monitoring in the eye, and it powers up by RF hitting it, and then it charges up a tiny little battery. So here's kind of a block diagram about what it is. There's a pressure sensor. There's some energy conversion. So this really is everything electrical engineering. I mean, it's radio, baseband, batteries, DC electronics. So I talk about the amount of power and the tiny little battery that's in there too, and they just show, there's a little picture of what the chip design is in the wireless transceiver for taking RF in to communicate, but also to charge the battery up so you can take a measurement. I was just intrigued by it because it's tiny, really tiny.
I just think it's interesting. So it's like we were able to just put those in there with like just an energy absorption system because we just emit so many different waves on a daily basis.
In this case,
Yeah.
This gets powered by the RF, let's see, what's it called?
So like they go in and charge it themselves.
Yeah, well, okay, smart cards. You might have a smart card. I worked on a patent infringement thing and learned more about smart cards, and I worked with some of that stuff. So they call it the interrogator in a smart card. You take your card up to something and get it close, and then RF induces from either low frequency or higher frequency, and that powers the chip, and then it is able to send back. So this is kind of that type of device. The interrogator is a wireless RF sending device rather than setting it on right next to it. So the RF comes in and interrogates that device, charges up the battery if it's not charged already, or to run long enough so that it can give a measurement, and then you take it away.
So it's not just on a daily basis.
Yeah.
Okay.
You're thinking of something else which is also very interested, and that's energy harvesting just due to motion in the air or vibrations. That's an interesting thing. I visited a company in Colorado Springs that makes CO detectors and smoke detectors, and they're interested in energy harvesting so that you could keep your smoke detector and CO detector running without having to put a battery in it.
Kind of just like a general range solar panel.
Yeah, but it's, instead of being solar, it's maybe micromechanical, something or another. It could be air charged from air currents. That's another fascinating thing to read up on if you're interested in that. Energy harvesting generally refers to micro machines or something that can just harvest ambient light, air currents, I don't know. Very low power devices though. So that's the end of this intro. And these slides are all on the website, so you can go look at them if you want to. So I wanted to do another demo. I am going to put up a hints page between now and Tuesday, but everything that we've got going on these first set of problems, I wrote some notes down. I have my book here. If you haven't looked at the problems, problem number 1 is just taking a two-sided line spectra and writing out the time domain representation. That's stuff that you did in 2610 and maybe reviewed again in 3205. Problem number 2 is finding out if two sinusoids are periodic. In the analog domain, a sinusoid is always periodic, but when you sum two sinusoids together, you don't necessarily have a periodic waveform. So if you wanted to have a picture drawn of it in, say, Python, you could draw a picture, but the math of it is very simple, and the problem hints at just saying it's periodic if both of the frequencies are rooted in a fundamental frequency through an integer relationship. And in terms of math, in NumPy, we have greatest common divisor, GCD, or something that I did with Wolfram Alpha, just typed in GCD, put in two numbers, 560 and 30, and it said, yep, the greatest common divisor is 10. So the fundamental frequency for 560 and 30 would be 10 hertz, and that's what that problem is asking you about. It's pretty straightforward. Third problem is just sifting properties of the delta function. We will talk about these things next week. Fourth problem is energy and power, determining if a signal is an energy signal or a power signal. And for that, you can look in the notes, not too far down into the introduction here. I talk about delta functions, sinusoids, singularity functions, but signal classification. So this blue box is kind of where we hang out, and we'll be utilizing that in particular. If we have a periodic signal, this is the key formula that you've seen before. You just have to integrate over one period the magnitude squared, and that will, and averaging by the period, and that will get you the power. And problem 5 is taking some energy signals and verifying that they are energy signals and sketching them. Those sketches can be done in Python. They're a good thing to crank up on. The very last problem is just finding the energy in a particular signal, and this is a special case that I put in that problem, number 6. It's not the one in the book, but lest you think that I'm not supporting you in any way, shape, or form, if you go into this problem chapter 2 notebook, you'll find that I have a lot of helps in here. So in particular, I have a little function here that will create a triangle wave, periodic triangle wave. And then I can draw a picture of it, and then I can square it and draw the picture of it squared. And then down here I isolate one period, so I can find the power by integrating one period of that. And then here I numerically integrate one period in Python by summing sample values and then multiplying by the time spacing. That's simple numerical integration, right? Just integrating something by taking values of the function, multiplying by delta t, and then adding up all those values, and that'll approximate the area under the curve. So something to be thinking about over the weekend. This is Thursday, so I have a few days to think about it. I will call out what we're going to do on Tuesday. What I'm going to ask you to turn in, and what I'll put on, what I'll be having on the quiz. And it's going to be highly dependent upon what I manage to cover on Tuesday. Am I disappointed I didn't cover any math too much yet? Not really, because I'm trying to get you motivated and get tuned into what this subject is about. It's fascinating to me. Engineering is fascinating. I don't know why more people don't want to do this, but you're here.
Because it's hard.
Well, yeah. Everybody says it's hard, but I've been doing it so long, I just say hard is okay. As a matter of fact, what is life? Is it easy or is it hard? I think life is hard, and it's kind of, we've been created that way. We're in a situation where it's not easy, it is hard. I mean,
Some people don't want to rise to the challenge.
yeah, well,
Did you say you embed the questions into the notebook, or because I didn't see the handout here?
embed equations.
No, and the notebook thing, are those the problem inside there, or?
Well, I just,
Handout. I couldn't find a handout on your webpage.
oh, okay. So where is that? If you go into the COM lecture and you go into chapter 2, I'm looking at this notebook right here. It's in a zip file. So that's what I'm looking at.
So it's inside the
You download it as a zip and then you unpack it, and that's why.
it's inside.
Yeah, I mean that notebook is in there. So that's why I challenged you last time with trying to get up and running with Python. And I will feel better if somebody comes and says I'm almost there, but I don't have it. I'll know that you're challenging yourself to get it up and running. You don't have to. You can just do the math, but I like having fun playing with something to kind of validate. I'm really big on self-validating, work the math out and then build a little simulation and validate that on your own to me is the greatest thing, because what do I do in industry? I have to produce results, but I have to test my results, so I write code and test what I'm doing. Well, I'm going to stop the video and then get this thing saved off for our one distant customer.